Today, we're going to look at vectors, which are quantities with magnitude and direction. And we'll look at these in contrast with scalars, which are just magnitude. We are going to be giving vectors names, just like we gave our scalars names. So we're going to want to use a different style for drawing the names of vectors versus drawing the names of scalars. So for scalars, we're going to use our traditional letters like X, Y, Z, A, B, C, just like that. But for vectors, we're going to put an arrow over the top of them to indicate that a quantity is a vector quantity. So if I name a vector V, I'll put an arrow over the top of it. So V, W. We can use whatever names we want. We could use A, B, and C for vectors, just like we can use A, B, and C for scalars. But we're just going to draw an arrow on top, and that'll indicate that we're dealing with a vector. So the arrow indicates vector. All right. So we have to learn how to do some things. We have to learn what the vector is going to represent, what's going to be required to represent in our vector, and how we can think about it. Then we're going to need to learn about operations on vectors. What kind of operations can we perform on vectors? What does it mean to add them, to multiply them, to, well, adding and multiplying. That's what we get. At least there's multiple kinds of multiplication. So we need to think about vector representation. How do we write them? How do we describe them graphically, algebraically? How we think about them verbally. And we also need to think about vector operations. All right. Yeah, we'll usually use lowercase. The question is vectors are small letters. We'll usually use lowercase letters to name vectors, just like we do with scalars. It's one of those weird math things, like we use capital letters for things like matrices, but we use capital letters in other scenarios as well, like to name vector spaces, which can get confusing because we study vector spaces at the same time we're studying matrices, and matrices are heavily used in the study of vector spaces, and we use the same kind of lettering for them. But at least here, we're making a distinction between vectors and scalars. All right, so let's talk about vector representation, and then we'll start talking about vector operations. So a vector is a quantity with magnitude and direction, and we usually visualize this with an arrow. So a vector has magnitude and direction. Two quantities, got magnitude and direction. And we usually represent these vectors with an arrow. And so this could be the vector V. Now, to describe the direction, we have a number of, we'll need a number of components equal to the dimension of the space that we're in. So we'll need a number of components equal to the dimension of the space that we're in. So in R2, a vector will need 2 components. In R3, a vector will need 3 components. In R4, a vector will need 4 components. Gets hard to picture at that point. So we can't be drawing things all the time, especially when we start getting into 3-dimensional things, and especially since you got me as your instructor and I can't draw stuff. So we don't need to draw stuff because we can visualize it with just values, with components. So in the category of vector representation, we'll need a number of components equal to the dimension of our space. So 2 in R2, 3 in R3. The usual thing to do, so let's say this vector v is in R2. The usual thing to do is to break it into horizontal and vertical components. So this vector v has a horizontal component. I don't think you can see the grid here, but and since we're this vector points from left to right, the horizontal component will be positive 2. And then we have a vertical component. You can't see the grid, but it is 3. And since the arrow is pointing up, our vertical component is positive 3. So there are these 2 parts of the vector that we need to describe. So this vector will have 2 scalars to describe it. And we have lots of ways of doing this. I could say this vector, since it's got a +2 horizontal and a +3 vertical, I could say that the vector v, one way we do this is to use pointy parentheses. So I'd say 2, 3. Where, and as usual, we list the horizontal component first. Right is usually positive and up is usually positive. So unless otherwise specified, that's the directions that we're going to go with. Other ways that we can represent vectors, this is just different ways that we can record the 2 components that we need to describe this vector. We could also say that this vector, we could also describe this in a vertical format, where I put the horizontal component first and we read from top to bottom. In this case, we're just writing them top to bottom. We don't need commas because we separate them with a line break. But since we're just writing numbers, we need to separate them with a comma, the components with a comma, because we just make bigger numbers by jamming digits together. The other way we can represent a vector is in terms of some, I'm going to use some linear algebra terminology here. It's the standard basis vectors, our unit horizontal and vertical components. So we can just divide R2 into horizontal and vertical unit vectors. So I could look at the vector I, and since it's a basis vector, I'll call it I hat. So you just draw an I with a little pointy hat on it. It's like a dunce cap, so it's a little bit insulting, but I don't think the vectors mind so much. And then we could describe this as 1, 0. Or we could describe I hat in vertical fashion as 1, 0. 1 horizontal, 0 vertical. And then the vertical unit vector will be j hat. And so that will be 0, 1, or in a vertical fashion, 0, 1. So using these basis vectors, we can describe V as 2 of this I hat we'll take 2 copies of I and 3 copies of J. So here are different ways that we can describe the vector V. Once again, we just need some kind of system for listing the components of the vector, a number of components equal to the dimension of our space. Way back in algebra, when we knew we were just going to have X and Y, we could describe this direction as 3/2, and then just make sure everybody agrees to say the change in Y divided by the change in X. From a function standpoint, that was most useful. We always make Y a function of X, even though we don't have to. We always did. And then so the 3/2 tells us what happens to Y when X increases by 1. But now that we're going to be moving into bigger spaces, I got to list the components separately. So we're going to start just with R2. Any questions? So note that by doing this, by writing this piece down here, that V is 2 I hat plus 3 J hat, I've kind of implied how the 2 operations work on vectors, the 2 simplest operations: scalar multiplication and vector addition. So this 2 I hat plus 3 J hat, writing it this way requires that we understand how scalar multiplication and vector addition work. So the question came up, can we also represent vectors horizontally at like 2, 3? We can, as long as it's very clear that we're talking about a vector and not a point in space. So to distinguish that, a common thing to do is, instead of using parentheses around the 2, 3, to use these pointy parentheses around the 2 and 3. But there are certainly times when I'm going to end up being lazy and I'm just going to put them in parentheses and hope that we're all agreed that these are vectors and not the point 2, 3. And we don't really have official names for these different forms. So whatever form the problem happens to be written in, just follow that tradition. It's kind of like when you're dealing with radicals, keep things in radical form. If you're given a problem in fraction exponents, stay in fraction exponents. If you're given rational expressions, stay rational expressions. If you're given negative exponents, continue to use negative exponents. Just kind of like match whatever is, however things are being represented at the time. So by writing this vector v as 2i plus 3j, we're indicating how scalar multiplication and vector addition work. Because I'm thinking of this v as 2 copies of the I vector and 3 copies of the j vector stacked end to end. So when we add vectors, wherever we start from, if I wanted to add a vector w to this v, I do go in the direction of v, and then whatever w says to do, I go in that direction, starting from the end of v. And I just tack them all together. And that's what I'm indicating here when I say v is 2i plus 3j. Because I'll take 2 copies of the I vector to make this vector v. I'll need 2 copies of the I vector. Just stacked end to end. And then onto the end of the 2 I vectors, I'll stack 3 j vectors. And that's where I'll put the end of v. So to add vectors, we just stack them end to end. When we multiply a vector by a scalar, we just make it longer. So scalar stretches out, changes the magnitude of the vector, and the vector addition could change the direction of the vector. So if I have this vector v, and I have another vector u, let's say the other vector u goes 4 in the horizontal and -1. Sorry, I just realized I just turned the whole page. So if I have 2 vectors v plus u and I want to add them together, I just stack them end to end. And so the vector v plus u will start at the beginning of v and go towards the end of u. So this is visually how we add vectors. Just put one vector on the end of the other vector. So what if we're not just visualizing our vectors? What if we have components? If the vector v that I use down here, the vector v that I use down here is 2i plus 3j. So if I say the vector v is, oh, I didn't leave myself space. If the vector v is 2i plus 3j, this vector u I set up as 1, 2, 3, 4. So u is 4i, but then it goes down 1, so -1 times j. Take a look what the vector v plus u is. So this is supposed to be 2. Look at the vector v plus u. I go 1, 2, 3, 4, 5, 6. horizontally, and then 2 vertically. So v plus u is 6i plus 2j. So now, vector addition seems like a very simple operation. Notice that all we did when we added v plus u is to add like terms, because that's just how adding works. We only add things that are the same, and when we add them, it doesn't change what they are. So v plus u is 2i plus 3j, there's the vector v, plus 4i minus 1j, there's the vector u, and we just combine like terms. 2i plus 4i is 6i, plus 3j minus 1j is plus 2j. If we had expressed the vectors in a horizontal or vertical fashion, we just add the corresponding components. So if I did 2, 3 plus 4, negative 1, I just add the first component, 2 and 4 is 6. 3 minus 1 is 2. So once we understand what we want to represent with vectors, vector addition and scalar multiplication work exactly how we think they should work. Vector addition and scalar multiplication work exactly how we would guess they work. They work just like we would have guessed. You add the corresponding components. If I ask you to add a couple of vectors with no other context, this is just what you would have guessed first. Unless our years of mathematical abuse making you feel bad for guessing things wrong keeps you from guessing. But that's the thing that we're trying to break out of. So can't be afraid to guess. It's all we got. Any questions? All right. So there's some other details of vectors that we need to talk about, some other pieces, some other terminology that we need to get through. Let's talk about the magnitude of a vector. So let's come up with a vector. Let's say v, and let's give it 3 components, since I'm not going to be drawing it. Let's say v is, there's an I component, a j component, and a k component. So if I is in R3, I is going to be 1, 0, 0, J will be 0, 1, 0, and K will be 0, 0, 1. That's how we just add another dimension to things. So if we want the length of this vector, we can imagine starting off at 0. If we start off at the origin, the point 0, 0, 0, then the end of this vector is at the point x, y, and z. The magnitude of this vector is just the distance between those 2 points. So the magnitude of v is going to be the square root of x squared plus y squared plus z squared. We're just going to extend the difference formula, or sorry, the distance formula to 3 dimensions. There is notation for this, of course, because this is math. Everything has to have notation. And for notation, the notation for the magnitude of v, it's like absolute value, but we put 2 absolute values around it. So that's the notation for the magnitude of v. It makes sense to use a variation of the absolute value because the absolute value is like the magnitude of a number. We don't care about the plus or minus, we just care about how much there is. We don't care what direction things are going. Those of you who move on to become math majors will stop saying this is exclusively just a length, and we'll call it a norm. A norm is just a generalized term for length. So the question is, what if we put an arrow on top of the basis vectors instead of a hat? That's fine, as long as you're putting something on top of the vectors to indicate that they are vectors and not scalars. Typically, if you use I, J, and K, in this environment, for the most part, people will understand that you're dealing with the vectors I, J, and K. We use I, the scalar, typically as an index. So x1, x2, x3, x4, so and so to xi up to xn and so forth. So we sometimes use I as an indexing, but it'll be clear in the context whether I is an index or whether I is the vector 1, 0, 0. Sometimes we will want to describe just a direction and not have to worry about magnitude. And the direction is not always in just the I, J, and K direction. So to describe a direction, we'll use unit vectors. To make a unit vector with a given direction, we just divide by the length or divide by the magnitude. So if I take the vector v, v has a particular length. If I just divide every component of v by its magnitude, so v over the magnitude of v is a unit vector. And unit vector means a magnitude of 1. It's a unit vector in the direction of v. Sometimes we need unit vectors going in strange directions. I guess it's not that strange. the non-standard directions, not horizontal or vertical. Sometimes we need unit vectors in a particular direction. So we just take a vector in that direction and divide by its length. That will give us a vector with a length of 1. So for example, if I had that vector in, I had the vector v, which was 2i plus 3j. If I find the magnitude of v, that'll be the square root of 2 squared plus 3 squared, will be the square root of 13. So if I divide v by the magnitude of v, I'll get a unit vector in the same direction as v. So and this is scalar multiplication. I just multiply everything by 1 over the square root of 13. This is a unit vector in the same direction as v. So the square root of 13 is more than 1. So if I had if I draw the vector v, which is 2i plus 3j, that has a magnitude of the square root of 13. So v over the magnitude of v is going to be in the same direction. Stick out. But has a length of 1. We got the same direction with a magnitude of 1. If we find the magnitude of this unit vector, this square root of 13 is just going to cancel out the square root of 13 that we ended up with at the end. But if we want to verify that, if we want to find the magnitude of this unit vector, we would just find the square roots of 2 over root 13 squared plus 3 over root 13 squared. So I have 4 over 13 plus 9 over 13. And then we'll take the square root, we'll add those together and we'll have the square root of 13 over 13, which is 1. I realized I was going to run out of space because I didn't put this down far enough. And so I kind of bailed on writing the calculation, just wrote equals 1. So this equals is kind of a, trust my calculations, which is a bad idea. Never trust my calculations. I'm very bad at arithmetic. Any questions? It's important that we start looking at vectors in all kinds of different ways, not just the ways we looked at them in physics, not just the ways that we looked at them in linear algebra, because here in multivariable calculus, we're going to be doing different things with vectors. So we're going to be drawing curves in R3. If we've got some curve running around in R3, I know it looks like this curve is running around in R2, but I assure you it's in R3. And let's suppose it's going in this direction. Then maybe at some point on the curve, we're going to want to ask a calculus question, which is like, what is the slope of the line tangent to this curve at a given point? So it might be that at this point, we'll be asking the question, what direction are we headed? What is the slope of the line tangent to that? We don't get to use slope because we're in R3 and we're going to have 3 components, but we're just going to want to find what's the tangent vector. We're also going to want to do some kind of integration along this curve in R3. So we're going to have to remember what integration is. Integration means we're just adding up values of the function over an interval. In single variable calculus, we're just adding up values of a function over an interval. So the integral from a to b of f of x to x is just a bunch of values of f of x from a to b. We could say we're adding up all the values of f of x between a and b, but there's an uncountable infinity of them. So we had to interpret that in a particular way, but we're just adding up values of the function. So along this path, we might just want to add up a bunch of values of the function along this path. We're going to have to think about what that means, but we're going to still use that base question, those 2 base questions at the very beginning of calculus. What's the slope of the line tangent to a curve at a point? And what's the area under a curve? What happens when we add up a bunch of values of the function? Any questions? Right. So what you are working on this week is going to be the problems in chapter 13. It's a bunch of vector problems. There are 2 more operations that we need to talk about. There are 2 operations that we need to talk, more operations we need to talk about, where we're multiplying vectors, multiplying a vector by another vector. And we're going to have to talk about what interpretations we get from those. So we got scalar multiplication, vector addition, and then 2 kinds of vector multiplication. It looks like I'm being informed that the chapter 13 assignments are at 3 attempts. So I am going to have to adjust those to unlimited attempts. If you already attempted the homework, this may mean resetting the homework. I did not know that those were still at 3 attempts. So I will adjust those to be unlimited attempts, which means you may have to go back and attempt them again, because I think doing that wipes out the previous assignment. So you're welcome. You get to do the problems again. I know it seems like a bad thing, but this is a good thing. You get to do more problems. That's how you got to start convincing yourself that this is a fun thing to do. It's not that you have to do problems, you get to do problems. It's not that you have to go to school today, you get to go to school today. You know what I mean?
Actually, there's science behind that. You can reroute that synapse.
Yeah.
It's proven.
It's proven. You can convince yourself that this is what you want to do. I recommend doing that for school. You need to convince yourself that you get to go to school, because I view school as a positive thing. You get to learn stuff. You get to expand your mind. I tend to not apply it to work. I find it very damaging if you apply that attitude towards work, because I don't view work in a positive light in general. There's a reason we all grumble about getting up and going to work. I want people to be happy to get up and go to school because it's an opportunity to learn things. But the way that we do work, where you have to have some kind of job so that you could do, what's it called? Live. I find that kind of anti-human and generally a very bad idea. But now I realize everybody's like, well, this is what we've always done. What we've always done is what got us here in the first place. So maybe we should start looking at some root causes and not just start putting band-aids on things. You know what I mean? And philosophically, I think about this a lot, but philosophically, I've come to the conclusion that at the root problem is that we just don't care about each other. And so maybe we should try to do that, do things where we do care about each other. You know what I mean? Not just friends and family. It's easy to care about your friends and family. That's easy. Do the hard part. Care about people that you don't even know. You know what I mean? Once we start defending and fighting for people that we don't even know, then we have a chance. Until then, the destruction of the human race through climate change is the right answer. So until we can actually start, giving a crap about people that we don't even know, that are super different from us too. You know what I mean? Anyway, I'm going to go in. I'm going to change so if you haven't started chapter 13, I'm going to change those. So don't start them before 10 o'clock today. I'm going to change those back to unlimited attempts. Work on chapter 13. If you're adventurous, do chapter 13.3 and 13.4 about dot product and cross product, even though we haven't talked about it in class yet. So that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.